In this video, we'll learn about organic reaction, especially for halogenoalkane. First of all, we're talking about preparation to make Rx or halogenoalkane. The first is free radical substitution of alkane by chlorine or bromine in UV light. The reaction happens between alkane and Cl2 to form RCl and byproduct HCl. The second way to make halogenoalkane is by electrophilic addition of an alkene with a halogen X2 or a hydrogen halide HX at room temperature. In this reaction, the double bond breaks and the Cl2 or X2 come into the C of the double bond. When the substituent or the addition species is HX, then the H from the HX will come into the carbon in the double bond with more hydrogen atom. The third way to make halogenoalkane is from alcohol, ROH, by substitution of OH with HX or PCl3 or PCl5 or thionyl chloride SOCl2. The product is OH substituted by X to form Rx plus the byproduct of PCl3 is H3PO3. For PCl5 is HCl and POCl3. For SOCl2, HCl plus SO2. When we use HCl, the byproduct is H2O. We continue with the reaction occurs to Rx. The reaction is nucleophilic substitution. First, Rx react with aqueous alkali, for example with NaOH. The X substituted by OH to form alcohol, ROH, and NaX. In the form of ion, OH minus, to form ROH and X minus. The presence of X minus can be identified by the addition of silver ion, then will form precipitate of AgX. For example, here we have bromoethane CH3CH2Br plus NaOH will form ethanol CH3CH2OH and NaBr. This reaction can be written as CH3CH2Br plus OH minus to form ethanol and Br minus. In this case, aqueous chlorides give a white precipitate of silver chloride Bromides give a cream precipitate or silver bromide, and iodides produce a pale yellow precipitate of silver iodide. We find that the fastest nucleophilic substitution reactions take place with the iodoalkanes. The slowest nucleophilic substitution reactions take place with the fluoroalkanes. The substitution reaction involves the breaking of the carbon-halogen bond. The bond energies in table 16.1 help us to explain the rates of reaction. Here we can see that the bond energy of C and I is the weakest, 228 kilojoule per mole, while the bond between C and F is the biggest, 467 kilojoule per mole. As we can remember, fluoroalkanes here less reactive than iodoalkanes is most reactive because of the strength of the carbon and the halogen bond getting weaker from fluorine to iodine. The other reaction can occur to a halogenoalkane is substitution with Cn- in ethanol. Rx plus Cn- to form RCN plus X-. For example, we have CH3, CH2, Cl plus KCN, then we'll produce CH3, CH2, Cn, the Cn substituted Cl plus K joined with Cl, KCl. So we have here propanethyl that the substance hydrolyzed into CH3, CH2, COOH. The substituent can also ammonia, Rx plus NH3 to form amine plus HX. For example, we have CH3Cl plus NH3 in ethanol to form CH3 NH2 plus HCl. So we have here methyl amine or amino methane. For halogenoalkane, there were three types. The first is primary, when the halogen X attached to carbon atom with only one C attached to. For example, ethyl chloride is a primary halogenoalkane because the Cl attached to this C and this C attached to only one C. The secondary, for example, we have here 2-chloropropane, where the Cl attached to this C attached to this C and this C. So this is a secondary carbon. For the tertiary halogenoalkane is when the X or halogen attached to carbon that attached to 3 carbon atom. For example, here the simplest, we have 2-chloro, 2-methyl propane because 3 carbon atom. Then the mechanism of the nucleophilic substitution of Rx will depend on the type of the halogenoalkane. For the primary halogenoalkane, the mechanism is SN2. S is substitution and is nucleophilic. 2 is that the rate of reaction depends on 2 species. Here, for example, the nucleophilic substitution of Br by OH minus. The rate of reaction depends both on OH minus concentration and ethyl bromide concentration. For tertiary halogenoalkane, the mechanism is SN1. 1 meaning that the rate of reaction depends only on one species. In this case, depends on the halogenoalkane because the first step is the detach of halogen into halide and carbocation that will grab by the nucleophilic, and the process is fast. The trend in the stability of primary, secondary, and tertiary carbocations, the tertiary is the most stable, and then followed by secondary, and the least stable is the primary carbocation. Besides nucleophilic substitution, halogenoalkane can undergo elimination reactions. For example, with NaOH in ethanol and heating, the X and the hydrogen will leave the molecule to form an alkene. For example, we have CH3 CH2Cl plus NaOH in ethanol, and then heating. The Cl attached to the C will leave the molecule, and then the H from the next carbon will leave the molecule to form an alkene plus H from here, Cl from here to form HCl. The HCl react with NaOH to form NaCl.